Good morning, students. In today's lecture, we are going to learn the Clausius-Clapeyron equation, and which is useful for the study of the phase diagram between liquid and the vapor. And from this, we can go on determination of the delta HV, that is the enthalpy of vaporization or heat of vaporization. Now, the mixtures of volatile liquids dash vapor pressure diagram. So, we have taken the liquid vapor system, and for this we are going to find out delta HV. So, Clausius-Clapeyron equation is here. For any liquid at a given temperature, the amount of heat required for vaporization per given weight of the liquid is a definite quantity known as the heat of vaporization delta HV of liquid. And delta HV is equal to HV minus HL. Here HV is for vapor and HL for liquid. That means heat of vaporization minus heat of liquid. This is the HV and HL. So consider the system liquid and vapor. Now the Clapeyron equation for transformation of phase is, as we have seen already, the Clapeyron equation only. In today's lecture, we are going to see the Clausius-Clapeyron equation. So, before that, we have seen Clapeyron equation dP by dt is equal to del HV divided by T into Vb minus Va. And this is our equation number 1. So here dP is the change in pressure, dt is the change in temperature, delta HV is the heat of vaporization or enthalpy of vaporization, T is the temperature, and Vb is the volume of the B phase, and Va is the volume of the A phase. So suppose consider Vb is equal to Vg and Va is equal to Vl. That means Vb is the volume of the gas phase and Va is the volume of the liquid phase. So our equation 1 will become, instead of Vb and Va, we are going to put now Vj and Vl. So just after putting these values in equation 1 will become dP by dt is equal to del HV divided by T as it is in the bracket Vg minus Vl. So this is our equation number 2 now. Now, molar volume of the substance in the vapor state is very large as compared to the volume of the same mass of liquid. So, obviously we know that liquid has a greater intermolecular force of attraction as compared to vapor. But the volume of the liquid is less than the volume of the gas. Obviously, gas occupies the more space of volume. So, as we know that the Vg is very greater than Vl, that is volume of the gas is very greater than volume of the liquid. So, our equation 2 can be written as dP by dt is equal to del HV divided by T into Vg. When Vg is very greater than Vl, we can neglect the Vl in equation 2. So, equation 2 only remains del HV by TVg. So, I have written here equation dP by dt is equal to del HV divided by T into Vg. This is equation number 3. If pressure behaves ideally, or the vapor which behaves ideally, then for 1 mole of vapor, P into Vg is equal to RT. As our Boyle's law is PV is equal to nRT. So instead of V, we can put Vg, and number of moles are N, and for ideal gas, number of moles have 1. So PV is equal to nRT. Put N is equal to 1 and V is equal to Vg. So equation will become PVG is equal to RT. Here G is the suffix for gas. So just rearrange equation and find out the equation of Vg, that is volume of the gas. So Vg is equal to RT upon pressure. This is our equation number 4. Now put this equation number 4 in equation number 3 and we get dp by dt is equal to del hv into del hv divided by t into RT upon p. So p will get to above. So dp by dt is equal to p into delta hv divided by RT square. So this is our new equation. Now dp by dt is equal to p into delta hv divided by RT square. This is the final equation. Now we will see the next equation, 1 upon dt. So just take a derivation, 1 upon dt into dp by p. Just transfer this p to the left side. 1 upon dt into dp by p is equal to del hv divided by RT square. Now this is our equation number 5. Just split this equation as 1 upon dt into dp upon this p comes to the left side. Now d ln p divided by dt. dp by p can be written as d natural logarithm of pressure divided by dt is equal to del hv upon RT square. So this is our equation number 6, and equation number 6 also known as Clausius-Clapeyron equation. Now we are putting limits. So just put limits to the left side, d ln of p, and limits are integration goes from p1 to p2 is equal to del hv upon r. These are the constant terms taken to the left. In integration dt upon t square, and limits are t1 to t2. Now just putting our integration values, the equation will come ln of p2 upon p1 is equal to del hv upon r in the bracket minus 1 upon t, and just put limits t1 to t2. Now ln of p2 upon p1 is equal to del hv upon r in a bracket t2 minus t1 divided by t1 t2. So after putting the limits, the equation will come ln of p2 upon p1 is equal to del hv upon r in a bracket t2 minus t1 divided by t1 into t2. So log of p2 upon p1 is equal to delta hv divided by 2.303 r in bracket t2 minus t1 divided by t1 into t2. So here to the left side ln is there, then we can convert it into the log form. So 2.303 log p2 upon p1, such type of equation will come, and we have transferred this 2.303 value to the right side. And this is the common form of a Clausius-Clapeyron equation. And this equation is very useful for calculation of the delta HV, that is the heat of vaporization or the enthalpy of the vaporization. And when we plot the graph of this equation, it will come as log of P versus 1 upon T. So log of P is on y-axis, 1 upon T is on the x-axis. So the slope of the graph is m, and it will come minus del hv divided by 2.303 r. So del hv is equal to minus 2.303 r into slope. And now log of pressure is equal to del hv divided by 2.303 into minus 1 upon t plus c is a constant, divided by 2.303. So this equation follows the straight line equation rule, y is equal to mx plus c. So keep in mind, for solving the problems you have to use this equation only. So this is a Clausius-Clapeyron equation, and this is a common form of this equation. Now we will solve one problem based on this. So Boiling point of water is suppose 100 degrees Celsius. Under what pressure will water boil at 102 degrees Celsius? Heat of vaporization of water is 2259 joule per gram. So boiling point of water is given 100 degrees Celsius, but we have to find out the pressure, and its elevation point is given 102 degree Celsius, and del HV is given 2259 joules per gram. So initially you have to write the given things. So HV is given here, heat of vaporization, and it is a 2259 joules per gram. So just convert it into joule per mole. So water's weight, its mass is 18, just multiply it and it will come 40662 joule per mole. Now log of P2 upon P1, just write the Clausius-Clapeyron equation here. Log of P2 upon P1 is equal to del HV divided by 2.303 R into T2 minus T1 divided by T1 into T2. So just put values of T1 is equal to 100 degrees Celsius, that is 373 Kelvin, and T2 is equal to 102 degrees Celsius, that is 375 Kelvin, and pressure is 760 millimeter. Now we have to find out P2. So put all the values in this equation, and I have written all the values here. Log of P2 upon 760 is equal to 40662 joule per mole divided by 2.303 into 8.314 joule per Kelvin per mole, and temperatures are 375 minus 373 divided by 375 into 373. So after calculating this, we have to value of the right side is 0.03037, and here left side is as it is, log of P2 upon 760. So just transfer the log to the right side, that means take anti-log of the right side. So P2 upon 760 is equal to anti-log of 0.03037. So after taking value it comes 1.0730, and just find out value of P2. So P2 is equal to 1.0730 into 760. So pressure will be P2 is equal to 815.5 millimeter. So this is our pressure which we have found for the elevation of boiling point. So when 100 degrees Celsius is the boiling point, obviously pressure is 760 millimeter, but when the elevation boiling point at 102 degrees Celsius, the pressure will be 815.5 millimeter. So you can solve such a type of problems and try to solve the equation of the Clausius-Clapeyron on your own.